Okay, good afternoon, everyone. This is Chuck Marzak here from the National Institute of Standards and Technology. I'm very glad to be part of this course on soft matter science. And the lecture today, what I will present, is a discussion of neutron reflectometry. And the talk is broken into 4 parts. And at the end of each part, if you have any questions, please ask the questions then. You can type them in via chat, and I will repeat the question verbally and try to give an answer. So I will present today, as I said, something about neutron reflectometry, and if we do not have time to finish the material in this particular time slot, I will continue the rest of the lecture on Friday before the second lecture on polarized neutrons. Okay, so my career has, I've spent a lot of time doing neutron reflectometry, but I have learned a tremendous amount from all of the wonderful colleagues I've had over the years. So what I present today is in large part from about what I've learned from these collaborators of mine. So if you have any questions, ask them at the end of each of the 4 parts, and I think that we're ready to begin. So here are the 4 parts of this presentation. 4 parts, the first part of which will focus on basic reflectometry concepts. What is reflectometry about? Why does it have a special connotation? What is different about it than, say, diffraction? Okay, part 2 will discuss something about neutron wave characteristics and coherence. After all, if we're going to use neutrons to study materials, the structure of materials, and we're interested in getting accurate information, then we really need to know something about the probe that we're using to study the materials with, obviously. In fact, it's so important that we will devote part 3 to a discussion of the phase problem about direct inversion and simultaneous fitting. Diffraction, how does it relate to real space imaging? In certain circumstances, in fact, there is a direct connection, and we get almost an image directly if we have phase information. And part 4, which is probably very important to most of you doing studies of the structure of materials in a microscopic scale, we'll talk about applications of neutron reflectometry. Now, originally I was going to include X-ray reflectometry, but I decided not to, only in the sense that we have time to focus more on neutron part, but you should keep in mind that almost everything we say about the technique and the methodology for neutron reflectometry also applies to X-ray reflectivity studies as well. The big difference being that almost all materials that are studied with X-rays, we need to take into account a much larger absorption. So there will be an imaginary part to the scattering length density, which we'll discuss as we go along. Okay, so let's begin part 1. So in part 1, we will discuss among some of these topics, among others. We'll be first discuss some generalities, then something about the scattering length density profile, what specular reflection is, what the wave particle behavior of the neutron, what consequences it has in our interpretation and analysis of the data we collect about the structure of an object, about a condensed matter system, something about coherence length and how it pertains to the diffraction process in the context of reflectivity measurements. We'll discuss the resolutions, both spatial and in reciprocal or scattering space, and discuss non-specular scattering as well. So, one of the first things to keep in mind is that a very special condition exists called the specular condition, where the angle of incidence is equal to the angle of reflection. And as we will discuss in more detail, this means basically that the momentum transfer of the neutron with the object it's scattering from is normal to the surface. And we will be concentrating on systems that are in thin film or layered film form that have a morphology that's planar. And in this special geometry, the wave vector transfer being normal, the momentum transfer being normal, means that we are sensitive to the variation in scattering length density normal to the surface. So we get kind of a depth profile, like an archaeological dig through layered strata. And with polarized neutrons, as we'll discuss in the second lecture on Friday, we get not only the composition, the chemical composition profile, but also the vector magnetization profile, both the magnitude of the magnetization in the magnetic material, but also the vector directions of the magnetization as a function of depth. And as you all well know and have heard many times by now, that one of the big advantages of using neutrons as opposed to X-rays or electrons is that neutrons interact with the nuclei, and therefore they see a big difference in scattering power between, for example, the isotopes of hydrogen and deuterium, which make it very useful for studies of condensed matter, soft condensed matter, which is largely composed of hydrogen. It's also a non-destructive probe and can penetrate large macroscopic distances in single crystal substrates so that we can build cells that enable us to study films in direct contact with aqueous reservoirs, batteries, fuel cells, liquid cells with biological membranes on the surface, and so on. And because the interaction is relatively weak, again, just to reiterate what Sunny talked about, I'm sure, in the first set of lectures, the weakness of this interaction makes it possible to very accurately describe via theory what scattering is going on and how to analyze the data. Okay. Now, it's very important. I'm sure if you were to ask an electron microscopist, it's great to have the latest electron microscope to do your research with, but a huge portion of the experimental process is devoted to properly preparing a sample. And that is also true for neutron reflection and scattering studies in general as well. And it turns out for thin film systems, for hard condensed matter at least, techniques like molecular beam epitaxy and other physical vapor deposition and chemical vapor deposition techniques enable people to make samples that are accurate on an atomic level, layer by layer. And this enables one to tailor systems, as we'll see later on, probably more of this on Friday, that can be tuned to study particular systems of interest in a systematic way. But this can also be applied to soft condensed matter. People have spent a lot of time in learning how to tether biomembranes to flat surfaces with special chemistries using alkane thiol bonds between sulfur and gold films on the surface of a single crystal silicon substrate, for example, and so on. And as we'll study in one of the parts in particular of this discussion, you can employ, by creating reference layers, buried reference layers, you can incorporate reference layers that are outside of the structure that you're interested in studying, but act in such a way to provide phase information in the scattering process. Okay, so again, this is just to reiterate what I just said in more detail about the fact that in the specular reflection geometry, the forward and inverse scattering problems are directly solvable. And in fact, it's akin to imaging in the sense that there is a one-to-one correspondence between the reflection amplitude and the scattering length density profile if you obtain the phase information in that scattering process, so that you can recreate a direct image, an unambiguous, unique solution of what it is that you're scattering from. Okay, and it turns out that if that is the case, then the spatial resolution and accuracy of the scattering length density profile that you obtain is limited only by the degree to which you collect reflectivity data over, the highest wave vector transfer you can go to, and the statistical uncertainty in the data itself. Okay, so in this picture, at the very top, first of all, we define what reflectivity is, and it's simply the number of reflected neutrons divided by the number incident on a given object. And the specular condition is just that condition, as I've already said, that makes Q perpendicular to the surface, so that the angles of incidence of the K vectors, Ki and Kf, the angle of incidence and reflection are the same, so the momentum transfer is in this direction. And in specular reflection, as we'll see, we measure the scattering length density depth profile as a function of depth. Okay, so here is sort of a general schematic illustrating the whole process. We take as the incident neutron, for example, in discussion of the theory, for example, as a plane wave, which we will modify to more realistic plane wave packet type waveforms. But for the purposes of the theory, the plane wave description works remarkably well, and we will use it extensively. So a plane wave incident with these wave fronts of constant phase, incident on a sample at some angle theta, some fraction of that will be reflected at the same angle in the specular condition with Q normal to the surface, and by doing so, by collecting data as a function of Q or this glancing angle of incidence and reflection, if we collect the reflectivity data as a function of this wave vector transfer, we will obtain information from which we can obtain, by fitting or inversion, the scattering length density profile normal to the surface. And what this means is, suppose we have a lipid bilayer on this semi-infinite substrate surface, and this will, if we measure this reflectivity, we will obtain the average scattering length density across a plane perpendicular to Q as a function of depth. So we're slicing the sample in these horizontal planes such that we will get a value for each average, and we can plot that as a function of depth and get this so-called scattering length density depth profile. Okay, I think that's pretty clear. Here is an example of what these scattering length density profiles might look at for three simple systems. A series of spheres, monodisperse in diameter and composition on a surface, or cylindrical objects, or a lamellar configuration like was shown in the previous slide. And the scattering length densities normal to the surface, these depth profiles look parabolic in this case, a little bit more rounded in the case of the cylinders, and rectangular in the case of the lamellar structure, which I think is kind of intuitive. But I think you get the picture. Okay, so let's talk a little bit about the basics. And some of this will repeat what you've already learned, certainly mentioned in Sunil's lectures. But it's good to go through because there are certain peculiarities, certain special situations or circumstances regarding specular reflectometry that need to be addressed. So again, if we assume a plane incident wave and we write this mathematically as this exponential function, there is a characteristic wave vector in frequency and wavelength. And if we ask, how do we treat what happens, and we treat the wave, the neutron as a wave, and obeying the Schrödinger wave equation of motion, then it boils down to solve what happens in the reflection process, equating the energy before and after. So we have a conservation of energy that's represented by kinetic energy, potential energy, and total energy terms in the Schrödinger equation, as you may be familiar with already. And we have in a potential that's described in this continuum limit by the sum of the number, by the sums of these products of the numbers of atoms of type J per unit volume times the characteristic scattering length, and the product of which is a characteristic scattering power or scattering length density. The real part of this quantity, which may be complex, is connected with the scattering process. The imaginary part describes an absorption. And this is, as I mentioned earlier, much more important for X-rays typically than for neutrons. But in any case, it's perfectly general and we can treat both exactly. So in vacuum, there's just a kinetic energy of the free neutron approaching the material object that it's going to scatter from. And in the material medium, there is an additional potential energy that we describe in terms of this scattering length density rho. Imposing the condition that energy is conserved, we find the relationship between the wave vectors in the medium and outside the medium in terms of the scattering potential, scattering length density rho, and we can define a refractive index that incorporates the information about the potential that we're ultimately interested in finding out about. Okay, now let's talk about specular reflection in particular. It's a very special geometry, and Warren Burke has coined the phrase the slab geometry, meaning that we have a flat surface with a certain density profile normal to the surface. It can be a single slab or it can vary as a function of depth. But in any case, this particular geometry with the angles of incidence and reflection equal, and the density being a function of the z-axis only, this problem reduces nicely to a one-dimensional problem because the variations of the density in plane, in the x and y directions in this particular reference frame, these densities are constant. So there's the derivatives are zero, and these serve as constants of the motion in the equation, in the Schrödinger wave equation. So that this gives us, on factoring the wave function, a situation where the equation to be solved is a second-order linear differential equation involving z only, and it's a one-dimensional problem. So, in this case, it turns out, without going into this derivation in this particular derivation in detail, it's available in the appendix in what's denoted article pages, how we get the relation of the reflection amplitude as a function of wave vector transfer. The relation is an integral relation with the scattering length density profile, and it almost looks like a Fourier transform, except that the wave function inside the medium is very, very complicated in general. Now, what's usually done in many scattering situations, as you've already heard by now, if the scattering is weak enough, I can replace the wave function inside the medium with the plane wave solution in the vacuum, and if I do so, it gets incorporated into the exponential, and it's e to the iqz now, and we have a Fourier transform relationship between the reflection amplitude. This is not the reflectivity now, this is not the square. This relationship is the basis of most analysis of diffraction data that is in the limit where the scattering is sufficiently weak. Well, that's nice, and I just point out here again that even if the surface is not perfectly homogeneous in plane, if it's sufficiently small variation compared to the variation as a function of depth, then what we really measure is the average scattering length density in plane. And we'll say more about this later. And we can still get a legitimate reflection, specular reflection relationship that gives us the scattering length density profile for this averaged, in plane averaged quantity. Now, the problem is that in reflectometry, it's a little bit paradoxical that even though the scattering is relatively weak, at the very low angles of incidence, where Q is very small, the reflectivity in fact becomes very large. And there is a critical angle region below which the reflectivity is in fact unity. It's like looking in the mirror in your bathroom in the morning when you get up to shave or wash up or whatever. Everything incident is reflected. And so the penetration depth turns out to be only a few hundred angstroms, and there's very limited information that you obtain about the depth profile in this regime. But since the scattering is so strong there, the Born approximation, which assumes that the wave function is not very significantly distorted entering the medium, is in fact not very good approximation at all. And you can see plotted here is the exact solution of that equation, taking into account the strong scattering, these so-called refractive effects, compared to the Born approximation. And you can see that there are, the differences are as large as several orders of magnitude, and it's just hopelessly inaccurate and cannot be used in most situations to describe specular reflectivity. Because, after all, to get this composition scattering length density depth profile, we need to collect data, scattering data over the whole range of wave vector transfers, including those transfers near zero. So to get an accurate picture here, we need to have this measured accurately as well. So we're sort of back to square one. We have to solve this, albeit relatively simple-looking, one-dimensional Schrodinger equation, but we have to do it exactly. The Born approximation does not suffice. So if any of you have taken quantum mechanics courses, usually in the beginning, the very start of the course, you will learn something about scattering in one dimension from rectangular barriers or troughs or other simple objects in one dimension. And one of the techniques for solving such a problem is to impose boundary conditions on the wave function psi and its first derivative at every boundary that you encounter, where the potential changes from some constant value to something else. If you impose these two conditions, which relate to the conservation of momentum and particle number, it gives you a set of linear equations that can be solved, which relate the transmission amplitude on the right-hand side of the object that you're scattering from, and the reflection and incident amplitudes on the left, through what is known as a transfer matrix. So the transmission amplitude, the incident amplitude, taken to be unity here, and the reflection amplitude are all related by these matrix elements, which turn out to be what contains the information about the potential itself. All of these elements are made up of quantities containing the refractive index, the scattering length density values of that material layered structure. And better yet, we can treat any arbitrary structure to any arbitrary degree of accuracy by slicing it into small pieces, like taking a loaf of bread and slicing it into pieces, into slices that are constant scattering length density over some arbitrarily small thickness, let's say delta. And so it turns out that the transfer matrix in this linear set of simultaneous equations that represents the entire object is just made up of a product of the simple transfer matrices that correspond to each individual slice. And again, each individual slice contains in the argument of these trigonometric functions the refractive index and therefore the scattering length density that's constant in that slice. And so we can render any complicated object into a system that can be readily numerically solved. Okay, and the result is that the transmission and reflection amplitudes are related to these composite transfer matrix coefficients via these simple formulas, and this lends itself to fitting programs that you can use for relating the measured reflectivity as a function of Q to a model system until you get convergence to the model that best describes the measured data. So here, let's talk a little bit about some simple cases. Well, the simplest case, probably, that comes to mind is this, rectangular barrier, just an object that has a very flat, sharp, abrupt interface that's semi-infinite in extent. Now here the scattering length density is constant, and what happens is that the reflectivity is unity, as I mentioned earlier, up to some critical angle that's related to the scattering length density. So this critical Q is the square root of 16 pi times the scattering length density of that barrier, of this semi-infinite medium. Then, after this critical angle, the reflectivity falls off as 1 over to the Q4th, the so-called famous Poirot law that's well known in small angle scattering. So there's one type of scattering that occurs, the simplest case. You can solve this, as you see in the upper right-hand corner, analytically from this situation. Now, if that interface to the semi-infinite medium is not quite rectangular, is rough, then this makes the reflectivity, if you render this into small slices and solve the reflectivity equations, again, and model this, you will find that the reflectivity falls off even faster than 1 over the Q to the 4th. And the degree to which it falls off faster is an indication of the RMS value of the surface roughness. So this is very useful to measure the surface roughness of such a system by looking at the specular reflectivity. Now, suppose we have a medium that has a beginning and an end, a front and a back. Then, well, the fact that we're scattering from this with a wave, we're going to get some interference of waves, between waves scattered from, let's say, the front surface and the back surface, and there'll be destructive interference and constructive and so on in a periodic fashion, and these oscillations that are observed in the reflectivity as a function of Q are the so-called Kiesig fringes. Then it turns out, as you would expect in the diffraction process, that where the scattering space or reciprocal space is related to the real space object by an inverse connection, and so 2 pi over the periodicity of these fringes is equivalent to the thickness of this material. If we have a more complicated system, say a multi-layer, in this case are shown triangular types of scattering length density variation, again, as a function of depth into the surface, then you will get 2 pi over that particular real space period. You will get peaks in the reflectivity profile as a function of Q. And that's pretty straightforward stuff. Okay, what is this sensitivity? What can we typically measure with neutron reflectometry in the specular condition? Well, it turns out that it's possible with the state-of-the-art reflectometers at various facilities around the world to get down to about 10 to the 8, almost 10 to the minus 9 in some ideal situations in reflectivity. That's many orders of magnitude. But again, we need to collect reflectivity over such a range to be able to get the full scattering length density depth profile picture with a resolution that's 2 pi over that maximum Q that we can measure to, so that to get, let's say, something like 0.5 nanometer spatial resolution in these profiles, we need to measure out to almost 7 reciprocal angstroms in wave vector transfer. And I'll show you a case later on in part 4 where that has in fact been done for a biological system. Okay, as in all scattering techniques, we have to remember that what you measure depends on the characteristics of the beams that you're using to study the sample with, and that if the beam has a finite angular divergence in energy bandwidth, then we have to fold the exact calculated reflectivity as a function of Q for a model system at a given wavelength and angle of incidence with the distribution that the beam represents, and then do this, so there's this convolution of the actual measured, the convolution of the real reflectivity corresponding to this particular multi-layered system with the distribution that's represented by the beam. And of course, the sample itself is effectively part of the instrumental beam resolution component, because if it's curved, obviously a neutron incident at this location is at a different angle if the surface is curved than for a neutron incident, even though it's parallel, at a location further down the substrate where the angle is different. So this has to be taken into, curvature of the substrate has to be taken into account as part of that instrumental incoherent beam resolution. And of course, the flatter the substrate, the less this contributes and degrades the the less it degrades the resolution. So flat is good. It's flatlined. Now, as I mentioned earlier, probably more than once now, to measure some particular feature in the scattering length density profile with some particular length scale, let's say a few angstroms, then we need to go measure the reflectivity curve continuously all the way out to some value that's roughly 2 pi over the characteristic feature length. Okay, but it also turns out for certain systems, like a thin film with a front and a back, that to get other quantities, for example, the total thickness of the film, because of this very strong interference between the front and back reflected components of the reflected beam, wave function rather, it turns out that these minima, locations of these minima, are very accurate indicators of the overall thickness. So it's kind of, again, paradoxical in the sense that to get some very detailed information in length scale about certain features, you need to go to very high Q, but you don't need to go to such high Q if you just want to extract information such as the total thickness of the film. That can be found at the first minima to very high accuracy to a few angstrom accuracy. So just a peculiarity is sort of that I just want to call to your attention. Okay. Moving right along, here is a typical reflectivity curve, neutron reflectivity curve on a log scale that corresponds to this biological membrane system that's frequently as a generic version of systems that are very often studied by biologists. So on the left, in this scattering length density profile, we have a silicon substrate that's, again, semi-infinite in extent all the way to the left. There's a chromium pre-wetting layer and a gold film, and then there is a chain, a lipid layer chain that's attached to this gold surface via an alkane thiol structure. The bond between sulfur and gold is very, very strong. And so you can secure this very thin, of the order of 50 angstrom lipid bilayer to the surface, and then deuterate one leaflet, the upper part of the bilayer, and the lower part of the bilayer can be hydrogenated, and that gives us very large scattering length density contrast. And this can be placed in close proximity adjacent to an aqueous reservoir, for example, or whatever. Okay, but suppose we ask the question, what can we realistically expect to resolve in this structure? And there are head groups here on this end and this end, and the tails are in between. And if there is some variation in the scattering density of the head groups, say that looks something like this, then how far out in Q do we have to go to be able to resolve this structure from just something that is much more spread out and not resolved? Well, if I go out to a Q of 0.3, for example, then this dotted line here shows us that, well, that's not quite sufficient. There's kind of a shoulder here, but it's not sufficient to resolve this variation in scattering length density. To be able to do that, we really need to go out to something like a Q of 0.6, where we can now start to see this distinct change in scattering density in this variation in the head group here from the tail. And that's what it takes. So again, to get a resolution of the order of, let's say, 3 angstroms, we have to go to a Q of 1. To get something of the order of 5 angstroms, we need to go to a Q of 0.6, and so on and so forth. Okay, we'll see an example of a real system later on. And that just gives you an idea of what's possible at the present time. Just one reminder that, again, reflectometry is still elastic diffraction. It's just in a regime of length scales at low wave vector transfers where we can treat the scattering length, the atomic system, the atomic constituents of whatever film we're looking at as a continuum. We can describe the scattering length density and refractive index that we talked about. If we continue to go further out in Q, we will run into the diffraction, so-called diffraction regime, where we are sensitive to interatomic spacings. We have to treat the material as being composed of point scatterers. And then we construct the structure factor that describes this accordingly. Okay, now just a word about non-specular scattering. If we tilt the wave vector transfer off the normal to the surface so that the angles of incidence and reflection are not the same, so the specular condition is not satisfied, then we begin to probe in-plane variations in the scattering density because we have a component of the momentum transfer now lying parallel to the surface. And so if we come off the specular ridge in the perpendicular direction, we will begin to see structure along this in-plane, let's say X or Y direction, that gives us information about periodicity or other kinds of variation in the density in the surface. So here's a simple example. These are grooves etched into the surface of a perfect single silicon crystal with a well-defined periodicity. And if we were to do a non-specular, or let's say just a specular and non-specular scattering experiment with neutrons from that surface, with this structure on the surface, we would see both specular along the z direction, normal to the surface, a structure that corresponds to specular scattering, and off in the next direction we would find structures or scattering that corresponds to the period of the grading structure of these troughs and stripes. So again, there's a modulation along the specular condition, along the truncation rod, if you like to call it that. that corresponds to the Cusick fringes. The fact that there is a scattering density that on average across here is more than the vacuum, but less than the thickness, than in the scattering density that corresponds to the silicon substrate beneath. So this looks like a thin film, and it has a thickness periodicity that we see again along the specular direction in this, along the Z here, that's manifest also in the positions and intensities of the off-specular peaks that occur along the X direction in plane. Okay, now suppose somebody was interested in studying a diblock copolymer system. And diblock copolymers are hydrogenous objects, of course, and we can hydrogenate one part and deuterate another. Let's say I have polystyrene and polymethyl methacrylate diblock copolymer system. Make the polystyrene deuterated and the polymethyl methacrylate hydrogenated. We get a huge phase contrast. And then if we take that system and we deposit it on this silicon grating structure, this grooved structure, we may find that at the tops we get a lamellae structure that is normal to the surface, whereas in the blocks we may find a different combination. There may be an ordering direction below some ordering disordered transition in molecular weight that gives us stripes that are vertical here and horizontal in the middle, and so on and so forth. Just one possibility. If you look at the scattering from such a system, it's very much different than the silicon grating structure by itself. Now there is additional information, additional scattering that can be analyzed to determine, in fact, whether that picture of the lamellae ordering in the way that was shown in the preceding slide is in fact that way, or some other architecture. Okay, but you get the picture, I think. Off-specular gives you this information. Okay, so we're at the end of part one. Do we have any questions at this point? I'll be watching the chat box for a few minutes. If somebody has a question about the content of that first Now, as I said, we have to be really careful about knowing something about the probe that we're using to infer this information about the structure that we're interested in studying. So it turns out for neutrons, to make a long story short, the neutrons emanate from, usually from a reactor or spallation source, and interact with a moderator that's hydrogenous in such a way that the scattering is incoherent from that moderating material. So every neutron emerges incoherently, both spatially and temporally, and independently of all the other neutrons. So it's almost a perfect incoherent source. That means it's like Dirac said in his textbook, his famous quote, that the photon, in that case, that he was referring to, interferes with itself if it's from an incoherent source, and that's what we have here. We don't have a laser. We don't have highly correlated many-body states emerging from the source. We have single neutrons, one at a time. So every neutron interferes with itself in that object, independent of all the other neutrons in the beam. Okay? So if we were to go and collect neutron diffraction from, say, a double slit, just like is shown for this case of electron diffraction from a double slit in the slide, we would find a neutron in this position of the detector, then one here, one there. We could go and shut the reactor off. Go home. We don't do this. We work 24/7 when the reactor's running. But if we did do this and went home and got a good night's sleep and came back, turned the reactor back on and continued the experiment, eventually we would get a diffraction pattern. But this diffraction pattern occurs statistically only after we've collected a sufficient number of neutrons, a whole ensemble worth in the beam over a given period of time, that manifests, that data collectively manifests a diffraction pattern. But again, the mystery of quantum mechanics is that every neutron interferes with itself and the object in such a way that we collect this interference only at the end of many, many identical type measurements. Okay, now it's important to realize that even though a plane wave is mathematically extremely useful for our calculations in solution of the Schrodinger equation, the reality is that a plane wave extends infinitely far in all directions, and that is unrealistic. A neutron being used to scatter from a sample, let's say at the NIST, one of the NIST reflectometers, is not simultaneously extending and scattering from somebody's sample at ILL on one of their reflectometers. The neutron, even though it has wave-like properties, is localized. And this localization is achievable, for example, by modeling the neutron, has been done from the beginning of quantum mechanics as a wave packet. You superimpose plane waves of slightly different k-vector values in magnitude and direction, and superimpose enough of them, for example, a Gaussian distribution of these plane wave eigenstates, and you get by this superposition a well-defined waveform that we call a wave packet that still has characteristic wave periodicity and some mean wave vector k and wavelength lambda, but it's now localized in space. It has a finite spatial extent. Now, this wave packet has to have a big enough extent that when it's diffracting from an object of dimension d, that it simultaneously sees the whole object. Otherwise, we would not see the diffraction characteristic of these this double slit that's measured on a detector, in a detector. But if we have a wave packet with the right characteristics, we can do our diffraction and have localization. We can have our cake and eat it too. So this is the approach that's taken. But this has implications, and let's discuss a little bit about that now. The biggest implication, I suppose, for reflectometry is that it's very important what the transverse extent of this plane wavefront in that wave packet is, the finite dimension here. Because suppose we have a sample that does have variations in plane in the scattering length density. Well, as we were discussing earlier, when we do the specular reflection measurement to get the scattering length density profile, we average in plane, and if this wavefront projected onto the surface is big enough, we can average, let's say, red and blue densities to get the purple average, and everything is fine and dandy, and we can connect this scattering length density to the reflection amplitude. Now, if that scattering length, if the transverse coherence or wavefront dimension as projected onto the surface only sees the red or the blue independently, one neutron at a time, then we get an incoherent sum that's weighted by the relative areas of the different densities on that surface. And we have to treat the analysis of that reflectivity appropriately if we're in the coherent case, or differently if we're in the incoherent limit. So this is very important to take into account and to remember. And I'll illustrate that here. Here is quickly our three profiles of a lipid bilayer, a single lipid layer, a bilayer, and then a coherent average of these two systems with 50-50 weightings. Now, this is the reflectivity from that, reflectivity from this. This is the reflectivity, one of these two curves, the red or the green, corresponds to this coherent average. The other curve here corresponds to the case where I don't average, and the coherent, and we have an incoherent sum of reflectivities 50% from this and 50% for that. Now suppose we don't know this ahead of time, and we go and do a reflectometry experiment. Then if we assume that we're averaging when we're not, and this is the case I've shown here, this is the curve, and I fit that, well, I can get a really nice fit. But it turns out that if that really corresponded to the incoherent average, and we don't know this, then the scattering length density profile that we get by modeling to fit this curve will correspond to something that's totally nonsensical and unphysical. It just isn't reality. So we get a result, even though the fit here is exquisitely good, we're fitting something unphysically. It's just not the correct analysis. So we have to be aware of this. So how do we know what to do? Okay, well, let's talk about how we find out what the coherence, transverse coherence length of the neutron is. Well, again, speeding through this, so we don't run out of too much time here, we can have these incoherent hydrogen sources in the moderator material, each from which emanate spherical waves that by the time they reach the sample many meters away have very planar wavefronts. And the fact is that the beam may be defined by an aperture that's bigger than these source points, clearly bigger than an atom. And so there's a complication here. We have an angular divergence that's defined by the apertures in some sense that tell us what the beam angular divergence is. And we have analyzer crystals that pick out a particular bandwidth that determine what the beam bandwidth is. But we also have to take into account the fact that the same optical elements and constituents of the moderating material, the hydrogen atoms, also define what the shape and extent of the wave packets are. At the same time, they're mixed together. So to be able to separate these two contributions, to see what the wave packet size and shape is, as well as the average or the distribution of average wave vectors associated with each of the constituent wave packets that make up the beam. To be able to do this, we can do experiments on well-defined periodic structures, for example, grating structures that have well-defined characteristic dimensions. So, for example, if the wavefront of the neutron is transverse component is big enough to average over many stripes and troughs, we get a single critical angle because we're just seeing one single average scattering length density in the specular reflectivity curve, one critical angle. But suppose that neutrons happen to have wave packets that have transverse dimensions or coherence that are smaller than the features, the trough, or the stripe, so that they see an incoherent, what we measure is an incoherent sum of reflectivities from the blue material and the gray, added together incoherently, then we will see two critical angles, one for one material, the gray or the blue, and one for the other. And this is for a 50-50 mixture of gray and blue, and we see two distinct critical angles, and in fact, this has been measured. And you could say here is the experimental result for the case where the neutron averages for a given periodicity. Here's the case where you have two critical angles and we're not averaging. So we can determine this. And it turns out that this dimension, this transverse coherence for a typical reflectometer is of the order of a micron. But its projection onto the plane, in at least one direction in plane, is multiplied by 1 over the sine of that angle. So it becomes very, very large. And it can be order of tens to 100 microns, which is good. So that in most cases, we average. Okay, here's a typical reflectometer at NIST. This is more complicated looking because it contains polarizing elements and spin rotating elements that are used for magnetic material studies, which we'll talk about on Friday. And we will try to do part 3 now. Okay, we have about 20 minutes left today, and we will try to cover part 3 about this other problem with reflectometry, the phase problem, which is a problem in all crystal diffraction, elastic diffraction, but which can be solved in this one-dimensional specular reflectivity condition exactly. It's one of the few mathematical models that has a one-to-one correspondence. Now, to be able to do this, to be able to unambiguously obtain a scattering length density profile from a given reflectivity, from a given sample, given model, scattering length density profile, we need to have the phase information, as we'll see. And we'll see how to deal with this. Okay, so here is a simple system. This is silicon substrate. This is titanium and titanium oxide in the scattering length density profile in an aqueous reservoir of water. This is the reflectivity curve, the circles, and the fits from this family of curves. So again, there's variation here because why? There is a finite value, a truncation of reflectivity data up to a certain maximum Q. So there's uncertainty. To get less variation here, we have to measure the higher Q. Okay, that's well and fine. We know that from this data, at least, it looks like the profile is somewhere within the bounds of this family of curves. Great. Okay, the problem is this was obtained by fitting a single reflectivity data set over and over and over again and getting families of this family of fits for the scattering length density profile have comparable goodness of fit chi-squared values. But if you continue to do this kind of parametric B-spline fitting, the search of parameter space, we find there's a whole nother family of curves that fit exactly, equally as well, this reflectivity data. Well, this profile is way different than that profile, and only one of these is physical and real. And this illustrates dramatically the problem with not having phase information. The phase of the wave is the yardstick, if you like. It's the flying ruler that's going up to our sample and measuring where the different scattering length densities in that material are located, how that scattering length density is distributed in real space. So without the ruler, we know there's material there that's scattering, but we don't know what order it's in necessarily. So what do we do about this? Well, we have to get the phase information. So again, what we just described was taking measured reflectivity data, or the amplitude squared, which is just the wave function squared, the intensity, reflected intensity, by trial and error, fitting it to some model to get a scattering length density, and we will sometimes find the right model, but we will also find sometimes profiles that don't correspond to reality because that phase information is missing. If we had the phase information, if we were able to measure the reflection amplitude, so you have the complex quantity, the real imaginary parts, then it turns out in this one-dimensional case for specular neutron reflection with no absorption, no appreciable absorption, there exists an integral equation solution, a glorified Fourier transform, if you like, called the Gelfand-Levitin-Marchenko solution that can be applied to give you from the measured reflection amplitude an exact, unique scattering length density profile, one-to-one correspondence. So, okay, to do this, to make use of that formalism, theoretical formalism, we need to have this phase. And it turns out, again, quickly going through this, if we use an interferometric or holographic technique where we have a buried reference layer that we know the scattering length density of, that's what reference means, we know it, and deposit the references, I'm sorry, on the right here, let's say a reference with a blue value, a green value, and a purple value of scattering length density next to this common unknown profile that we're interested in, and measure the reflectivity for this system, and this system, these three composite systems, get three reflectivity curves. It turns out that algebraically we can solve for the reflection amplitude, little r, this should be little r, that corresponds to that unknown layer, the red layer, the common unknown layer of interest, and it's an exact one-to-one correspondence at each and every Q, and we can get the reflection amplitude that way. So by using references, we have the reflection amplitude, real and imaginary parts. We can put these in the Gelfand-Levitin-Marchenko equation, or alternatively solve a differential equation developed by a mathematician named Sachs, and get the exact reflection, from that reflection amplitude, get the scattering length density profile. And here's an illustration. here is a system, an alkane file on with a lipid on next to aqueous reservoir on a gold surface, and where we changed the substrate from silicon to sapphire, repeated the experiment twice, got two, in this case, only two composite system reflectivities were necessary, and extracted from that exactly at each Q point the reflection amplitude. And this was inverted and gave us this profile shown in red. And this ringing that you see here in red, this physical is unphysical. This is a gold layer that's uniform scattering density, but this ringing comes from the finite truncation of the data. You go farther in Q, this ringing goes away. Okay, but it's remarkably close to this white curve, which represents the molecular dynamics simulation for this lipid system next to the aqueous reservoir. And so it really works. Also, it turns out that if you look at the imaginary part of the reflection amplitude that you obtain from such a measurement, without going into a lot of detail, the imaginary part has two roots, two solutions to a quadratic equation, and they have these characteristic. The solutions have sort of describe characteristic zero crossing point, zeros, that if the surface is not homogeneous in plane and you're not properly averaging, then you will get these gaps that occur. And this is an indicator, a diagnostic to tell you that you're not properly integrating in plane inhomogeneity. So it's just a useful tool. We'll talk about this more later on. Okay, but anyway, once you have a reflection amplitude, then you can rigorously, mathematically, and Norm Burke has worked this out, my colleague here at NIST, you can go from the uncertainties in the reflectivity data to finite truncation, or the truncation of the data to finite Q, the statistical uncertainty in each data point, and map from that an uncertainty in the scattering length density distribution that you actually measure by this phase inversion process. Very useful. So I'm just trying to emphasize, in certain situations, if the proper care and work care is taken and the work is done, you can in fact use specular neutron reflectometry with the phase determination method as almost a direct imaging, equivalent to a direct imaging in real space. Okay, we have about 15 minutes left. We're going to start on the applications, and then we'll continue. We'll go as far as we can go in 15 minutes, and then we'll pick this up on Friday and continue along with the polarized neutron discussion. So here it is. At this point, let me stop though, as I promised. Maybe I forgot at the last part, but if there are any questions, please ask now, and I'll wait to see if there is any. From Vince Chen, a very important question actually. He asks, what is the typical coherent volume of neutrons? It depends on how the neutrons are prepared. And in the specular neutron reflectometry condition, for a typical reflectometer that we have been talking about, it turns out that the transverse extent, the extent of the plane of the wavefront normal to the wave vector, turns out from the measurements that have been done here and at other places to be typically about 1 micron. Now the longitudinal length along the K vector is typically much longer than that, but for elastic diffraction, as long as it's sufficiently long to see the full thickness of the film, which it usually is, over 10,000 angstroms, then that length is much greater than the transverse length, and you can see this from the paraxial ray consideration. We don't have to worry about that so much. So the more important quantity, at least is in my experience, that we need to know is this transverse coherence length. So it's not so much the coherent volume, but the coherent transverse extent. The wavefront size or area perpendicular to the K vector of that wave packet. And that's about 1 micron. But remember, I pointed out that in the reflection geometry at relatively low glancing angles, there's an enhancement factor that comes from the sine of the angle, the projection of that wavefront onto the surface, that makes the effective averaging distance in the plane of the order of 10 to 100 microns, depending on what the angle is. But that's typical. I hope that answers your question, at least for now. If not, please email me and we'll go into more detail. Okay, thank you, Vince. Any other questions? We will take the last 10 minutes to start off on our applications. And we will fully cover this on Friday, so we don't miss any of the topics. So don't worry. Okay, let's start out in biology. Let's suppose we have a typical lipid bilayer system where we have a head group, tail to tail, heads opposing on opposite ends of the layer. These layers are typically 50 angstroms thick. And we are interested in some biological macromolecule, peptide, a protein, whatever, and how it interacts with that lipid bilayer. Now, on this length scale, in the tens of angstroms or less scale, this is something that really we need diffraction to be able to see. So, specular neutron reflectometry is an ideal probe, again, because of the possibility of hydrogenation and deuteration varying various parts of these constituents so that we can accelerate different parts of the structure. Here's a typical, this is just a model system that was done many years ago by Susan Kruger and Plant and Company at NIST. And this is a good example because it's a demonstration experiment, and not that melatonin is terribly important, it's a component of bee venom actually, I've learned. But it's illustrative of the power of the reflectometry technique, what its potential is. So suppose we have this gold surface sulfur bond with a lipid bilayer attached, and we want to know if we put in solution this melatonin molecule, where does it go? Does it not attach to the surface? Does it embed itself? Or does it really penetrate deeply into the lipid membrane? So clearly, to answer this question, if we were to slice across this system and measure the depth profile along this normal, we would find out where this stuff actually resides. So here's the beauty, again, of the neutron reflectometry technique. The neutrons will penetrate many centimeters, macroscopic distances, through perfect single crystal silicon, so we can take our substrate with the film on it, attach it, deposit it on the silicon substrate, put a gasket here, have a liquid aqueous reservoir in place adjacent to the film of interest, and introduce the melatonin molecules into that reservoir and study in situ where this melatonin actually goes as a function of pH, temperature, whatever. Here is data, reflectivity data, taken out to a really high Q. This is probably a world's record. I mean, this is really a difficult experiment to do, and it took a long time, a day and a half to do, of beam time. But it illustrates, again, what the potential is, what you ultimately can expect to get. And there's good signal-to-noise ratio all the way up to about 0.6 to 0.7 reciprocal angstroms. The black data, the squares, are melatonin, without melatonin, just a lipid bilayer by itself, and the blue dots are what the profile looks like after the introduction of melatonin. This is a log plot, but you can still see in many places in this profile there are dramatic, very large differences. This is absolutely amazing. Because, as I mentioned here, the sample area is something like this, but being such a thin sample, 50 angstroms, the total sample volume is of the order of a millionth of a cubic centimeter. And yet, we can see differences like this. This is really amazing. This is remarkable. Now, if you plot this in such a way that you multiply by q to the fourth, remember the Fresnel fall-off of 1 over the q to the fourth, this just accentuates where the differences are, and they're quite big. So if we go now, we analyze this data just by fitting in this particular case, we find that in this profile, the substrates to the left here, this is the sulfur on the top of the gold to the left. Here is the hydrogenated part of that leaflet, and this is the deuterated part, and you can see the difference between melatonin and with and without melatonin, that with the melatonin, there seems to be a dramatic change of the scattering length density profile right at the top in the upper head group. So the melatonin apparently nudges itself in the upper leaflet, and this is really clear indication of where it goes. And if you take and then analyze this system to get the composition profile, remember we measure the scattering length density profile. To measure composition profile, we do a little molecular dynamics simulation to relate those two quantities, and we get really good agreement between what the molecular dynamics expects. This is for the lipid bilayer system without the melatonin, by the way, and what we actually measure. And to be extra sure, well, let me first say that if we want to study systems that penetrate the layer, then we need a tethered layer structure so that we can have, let's say, a transmembrane protein actually penetrate through, and there's water on both sides of the lipid bilayer here. And David van der Rohe, NIST, and other people at ILL have perfected biochemical means of producing such structures. So the door is wide open to study all kinds of membrane protein systems. I'm just going to show you to end in the last 5 minutes some spectacular recent results that Frank Heinrich and Hirschnand and Matthias Loesch and company at NIST have gotten on various pathogenic protein entities and how they interact with the cell membrane represented by this lipid bilayer, this biomimetic layer. And they can see now in detail how some of these molecules extend out from the surface and tether to the top bilayer. Here's some of the representative data. You can look up some of these references and get the details. But it's just, in my view, this is just awesome. And this is the only way to get this information. This is very detailed with nanometer scale spatial resolution, and it's uncontrovertible that, again, they used reference techniques here and used multiple sets of data to make sure that there were no ambiguities in this case, to get phase information. And they clearly know how these molecules orient themselves. For example, this molecule certainly doesn't lay down on the surface. It extends outward. That's pretty clear from this study. So beginning on Friday, I'm going to pick up with an example, an application that sort of is a cross between a biomimetic or biological application and a polymer one. And what it's about is where water goes in this artificial coating that's used in synthetic veins, or would be used in synthetic veins and arteries. And the person that instigated this study was a vascular surgeon from Emory University, Elliot Chaikoff and company, who are interested in making coatings, synthetic veins and arteries for medical use in replacing defective veins and arteries in people. So we'll talk about this beginning of next lecture and continue with our applications and then go on to polarized neutrons. So are there any questions that anyone has up to this point? Even though we're not at the end of this part about the applications, please, if you have any questions now, feel free to ask. Thank you, Mayun, for the compliment. I hope everybody was able to learn something, as I have learned from all of my colleagues. But I see I now have a question from Clint. He asks, in the phase picture, slide 49, the two possible scenarios look to be inverted an opposite. Is this true, and is this related to the backside reflections? Actually, you're right. In the particular case that I showed for the titanium oxide, titanium film on silicon, those are symmetry-related profiles. And this is one danger always that you will have, because when you measure just the reflectivity, you can't distinguish front to back. You can reverse it, and you can't tell the difference. But there are more insidious changes that can occur that you might not expect that will give you ambiguous results, and we always have to be on our guard to make sure that if we suspect that the model that we're constructing of the system for which the reflectivity has been measured can have other variations, then we have to try to do an experiment where we can get some phase information or some other independent measurement, other technique that tells us, for example, which is the physical, which is the unphysical system. For example, in that case with the titanium oxide and titanium, it turns out that one of the profiles had a scattering length density that's not possible. It's higher than you could possibly have for those two constituents, titanium and oxygen. So in that case, it is true that somebody who knew that ahead of time could rule out one of those two possibilities. But that's not to say that there aren't other profiles close to those that might not be able to be ruled out without having the phase information. So it's just something that is good to have when you can get the phase information to be sure. Okay. Thank you, Clint, for the very good question. Another excellent question that really enhances the lectures. Thank you for asking, both you and Vince. If there are any other questions, go ahead and ask. If not, we will pick up on Friday. I'll wait a few more minutes. Okay, I guess there are no more questions. Thank you all for taking the time to listen, and I hope you're able to listen on Friday again. Thank you. Okay, I'm signing off. Goodbye.